Alright, now we will move on to our next section topic, which is the hydrostatic equation. Now, from the word itself, it says here static, which means that the fluid is not in motion. So no motion. When we say no motion, that goes true for both x, y, or z axis. So there's no motion if you consider, let's say this is a field or a space filled with a fluid, and if we consider an infinitesimal volume, right? So we'll see that there's going to be no shearing stresses on all the faces of this volume. Right, so if there's no shearing stresses, then meaning it's just static, and the force that's left is just the normal force, and this normal force will later you'll later realize that this normal force is just simply the pressure. And we will try to in this hydrostatic equation, it will describe the variation of pressure with respect to if it moves along the x or along the y, what's going to be the pressure, let's say the pressure relationship or the pressure function. Right, so if we move x, I mean if we consider a point along the y, along the vertical direction, then what's going to be the pressure? Does it change along the y? But if we consider any point along the x-axis, then does it change along the x-axis? So in this hydrostatic equation, we'll derive this first, and then we will describe the equation, or we'll explain the equation. Okay, so for now, let's consider an infinitesimal volume, right? So this is it. I'll draw it again. This time I'll try to draw it completely. Let's say this is our x, then this is our y, then this is our z. By the way, when we draw the coordinate system, it doesn't have to be always this in this direction. You can draw, like, for example, this is x, this is your y, and this is your z, as long as you follow the right hand rule. And therefore, if we derive an equation, it will be based on this orientation. Okay, so that's why you would see that in the different textbooks in fluid mechanics, you would see that sometimes they use z in this upward direction. So just take note of this. Just take note of the orientation from which the equation was derived. Okay, so we say that there is a force, there's a pressure, right? Let's say for now it's pressure. So we have pressure along this direction, and we'll also have pressure at the opposite direction. So let's say this is P sub z, and then this one would be P z plus dz. Okay, so why is it dz or why is it z? Alright, so this is our 0 point. Now from this point going here, the length of this cube is dz, right? That's actually dz, and the length of this side from the origin up to here, that's gonna be dx, and this one would be dy. Okay, so that's a differential volume. Okay, so we have forces on all the faces. So let's say this is px plus dx, and we'll write this is px, and of course this would be, this one would be py plus dy. Okay, so again, why is it plus dy? It's simply because my reference point is at the bottom. Right, so let's say this is my py at the bottom. Okay, so we can project this into a two-dimensional plane. Okay, and this will be x, and this will be y, and this will be our differential volume projected into a plane. Okay, so now let me rewrite it here. Okay, so this is our origin, this is our x, and then this is our y. And if we project the forces, what we get here, we have bx, and we have here bx plus bx. Okay, again, this length is dx, and this length is dy. Okay, so along the y direction, we have forces py plus dy. By the way, this is written as subscript, and here we have b sub y. Okay, so along the y direction, there's still also the weight of the fluid, right? So that's weight. Okay, so we see that since it's not moving at all, at this equilibrium condition, what we'll see that there's going to be an unbalanced force along the y-axis only, along the vertical axis, because here it will just cancel out because they're balanced, but along the y, there's going to be a difference. Okay, so now recall that pressure is equal to force over area, and therefore if we want to solve for force, that's going to be pressure times the area. Now this one is pressure, this one, all these are pressure, and we need to multiply that to the area because we want to apply the equilibrium equations so that we can derive a relationship. Okay, so this is the pressure, and I want to let's multiply the area. Now the area would be this one, the area that's perpendicular to the action of the force. So this area is, so we have this length, this is dz, and then this one is dx. So therefore, let's multiply this by dx dz, then this one by dx dz. Okay, so now let's apply the equilibrium. Now let's apply the equilibrium equation. So we'll apply the equilibrium equation along the y only. So summation of forces, right, so summation of forces y, and let's assume that upward is positive, is equal to 0. Okay, so meaning that all forces that's acting upward, that would be positive, and all the forces that's acting downward would be negative. Okay, so py times dx dz is equal to okay, so instead writing down the negative here, I just want to transpose it to the right side. So that's equal to w, the weight, plus the py plus dy times dx dz. Okay, so now I want to transpose this to the left hand side. So that's going to be py minus py plus dy is equal to the weight. Okay, so I just want to convert this to take this negative sign out, because this will be our point 2, this will be our point 1. Okay, so py plus dy, right, again that's subscript, py plus dy minus p sub y, that would be negative. This will be dx dz, so there must be dx dz right here, is equal to w. Okay, so we'll divide both sides by this dx dz and the negative sign. So therefore, py plus dy minus p sub y is equal to omega negative omega, sorry, that's the weight of the fluid, so minus weight all over dx dz. Now what is weight? Weight is just simply the unit weight. That's the weight density in Newton per meter cube. Right, so if this is Newton per meter cube, then we have to multiply the volume of this fluid, I mean of this differential element. Right, this is just simply dx dy dz. Okay, so this one we can just write the dp or delta p. We can just write delta p is equal to or we'll just write dp differential is minus omega times dx dy dz all over dx dz. Therefore you can cancel out this dx dz, and what's left is negative omega dy. Okay, so now this is the form. Now if we convert this to average values, that's going to be delta p is equal to negative the unit weight times the delta y. So take note that this delta y refers to the height, difference in height. Okay, so that's the reason why I emphasize this, that this equation, because sometimes in some textbooks you would see this delta z, just simply because the coordinate system that from which it was derived was this upward direction is the z-axis. But for us here, we use the y, so that's why it's delta y, or in some textbooks you just write h, or simply height. Okay, so now this is the hydrostatic equation in pressure difference form. In pressure change form. Okay, so it just says here that let's say we have let's break this down. P sub 2 minus P sub 1 is just simply the height, which is y sub 2 minus y sub 1. Right? So it says here that the change of pressure, that pressure varies in the y direction. Okay, so that's the reason why I've drawn earlier, let's say in the application to storage tanks, for example, that the pressure variation, let's say we have this fluid, right? This is fluid inside the container, and if we are trying to find the pressure here, that would be different from the pressure right here. Why? We'll have a linear variation of pressure, but along the, let's say along this pressure, let's say along this depth, so along this depth the pressure is just the same. Okay, but here again, so we have the same pressure across the x-axis, but along the y-axis it will vary linearly. Okay, so now let's try to translate the pressure change form into a head form. Okay, so as I've written earlier, that p sub 2 minus p sub 1 is equal to negative. And so if we divide both sides by the unit weight, we get p sub 2 minus p sub 2 all over this minus p sub 1 all over this, which is just equal to negative y sub 2 plus y sub 1. Okay, so I'll try to combine the conditions, the second conditions in this left side, and then the first conditions on the right side. Okay, so p sub 2 over this plus y sub 2 is equal to p sub 1 all over gamma plus y sub 1. Okay, so this is another form. It's what we call the head form of the hydrostatic equation. Okay, that's the head form. Why? Usually when you say head, that refers to, the unit would be in meter. Okay, so let's check that out. So this is pressure, p sub 2, that's Newton per meter squared, and this one is Newton per meter cube. So therefore, this one divided by this, what you get is in meters. So pressure sometimes is measured in unit of length. Okay, so this is the unit. So again, let me rewrite. So in pressure difference form, our equation is delta P is equal to negative the unit weight times the change in height. And then for the head form, we have p sub 2 all over this plus y sub 2 is equal to p sub 1 all over this plus y sub 1. This is what we call the head form. The unit right here is in, let's say, pascals, and this one is in meters. Okay, so the explanation of this head form is that this term right here is what we call the pressure head, and then this one is called the elevation head. Okay, again, this one is pressure head at point 1, then this one is elevation head at point 1, and the sum of this is what we call the piezometric head. This one too, piezometric head. So it says here that the sum of pressure head, let's say pressure head plus elevation head at point 1 or at point 2 is equal to the sum of the pressure head plus elevation head at point 1. So in other words, we can say that the piezometric head is constant. Right? Okay, so now let's do a sample problem regarding this pressure variation with respect to elevation. Okay, so problem 2.1. This is taken from the textbook. This textbook, Applied Fluid Mechanics by Mott and Antenner. Okay, so the problem says if a milk has a specific gravity of 1.08, what is the pressure at the bottom of a milk can? 650 mm deep. Okay, so let's convert this into a picture. Okay, so we have this can, and it says, right? Okay, so we have this can, and let's say it's filled with milk, and it says that the specific gravity is 1.08 Sg, and it's milk. Then the depth is 650 mm. Okay, 650 mm. Okay, so it says here what is the pressure at the bottom of the tank. Okay, so it doesn't say it is it has an open top or closed top, but what we're just given is this one, the 650 mm depth, that's the height, and this specific gravity. Okay, so first step is solve for the density or the specific weight Okay, so how do we solve that? That's just simply Sg is equal to the unit weight of the milk all over the unit weight of the reference fluid, which is water. Okay, so this one, the unit weight of milk, is just simply Sg times the unit weight of the reference fluid. So that is 1.08 times 9,810 kilogram. No, this is Newton per meter cube. That is 10,594.8 Newton per meter cube. Okay, so our reference is most likely this will be our reference point, and if that's the case, then solving now for the pressure at the bottom of the tank. Not tank, that should be can of the can. Okay, so we have this delta P is equal to negative the unit weight times the delta Y. So the change, if our reference is this line, let's say this is 0, then that's gonna be let's say P sub 2, this will be P sub 1, then this will be P sub 2, and let's assume that this one is 0 for now, because it doesn't say if it is open or not. If it is open, then it is subjected to atmospheric pressure. But since it doesn't say that it's open, then I think we can just assume that this reference line or reference point would be 0. Okay, so P sub 2 is negative 10,594.8. That's Newton per meter cube. Okay, times the delta Y. So if this is our point 1, this is our point 2, then our Y here, Y1 is 0, then this will be our Y sub 2 is equal to 650. Right, so 0.650, that's in meter. Okay, and that's going to be 6886.6 Newton per meter squared. Right, that's our P sub 2, and most likely this will be P gauge. Okay. Oh no. I guess this should be P gauge, which is just equal to 0, and then this one is another measurement if this is P gauge, but this one is 6,886.6 Newton per meter squared. Okay, so I'm not sure if this is atmospheric or not, but I guess it would be precise if we can we'll just assume for now that this is a gauge pressure. That's just where the pressure is 0, since it is our reference line, but it's not referring to the absolute. I think it doesn't refer to the absolute 0. Okay, so that's it. Okay, another one is for the tank as shown in the figure, determine the reading of the bottom pressure gauge in PSIG if the top of the tank is vented to the atmosphere and the depth of the oil H is 48.5 feet. Alright, so we have this container right here, and it says that this container is filled with oil, right? So this is oil, right? And this is the surface, and this is oil. This one is air. By the way, I guess we'll start with a simpler one, because this one involves interface. So it has a reading right here and then another pressure reading right here. So I guess we'll just first do a problem that's simpler than this one, but later on we will solve this. For now, let's consider this problem. Okay, a pressure gauge 6 meters above the bottom of the tank containing a liquid reads 90 kPa. Another height for meters reads 103 kPa. Determine the specific weight of the fluid. Okay, so basically this problem is just something like this, and this is your tank, and it says here that, let's say 2, 4, 6, 8, right? So for example, we have this fluid that's inside this container, and right here at 6 or at 4 meters we have a reading. Okay, so it says here that at 6 meters we have a reading of 90 kPa, and at 4 meters we have a reading of 103 kPa. Okay, so let's say this is our point 1, this is our reference point, and then this will be our point 2. So we can actually solve directly, because we know that the hydrostatic equation is P2 minus P sub 1 is equal to negative of the unit weight times the change in height, which is y sub 2, 4 meters, right? Let's just write y sub 2 minus y sub 1. Okay, so P sub 2 is 103 minus P sub 1, 90 kPa, is equal to negative this divided by y sub 2. So y sub 2 is 4 minus 6 meters. Therefore, our unit weight is 103 minus 90 divided by 2. That's negative 6.5 kilonewton per meter cube, or 6.5 kilonewton per meter cube. Okay, so we will do this problem in the next video. So as you can see in the first two problems that we had regarding the pressure variation, that's pretty straightforward, because you just apply the hydrostatic equations. But that would become complicated if we have a lot of interface like this, 2 fluids and there's an interface, or probably 3 fluids and things like that. Okay, so we will do this problem in the next video.